Hello everyone, welcome back. In this lecture, we shall see what is Y plus and different types of turbulence models. Y plus represents the non-dimensional distance or height of the first cell from the wall boundary. It determines if the mesh is fine enough near the walls to accurately capture the boundary layer. Okay, we shall see in detail. If we consider this mesh, the first cell height is given by Y and the non-dimensional representation of this first cell height is known as Y plus. We shall see in detail. Y plus is equal to y into u tau divided by nu, where y is the distance of the first node from the wall. This is the absolute distance, and u tau represents the frictional velocity. This is also equal to square root of tau omega by rho, where tau omega is the wall shear stress and rho is the density and nu is the kinematic viscosity. Okay, we shall see some more details about Y plus and turbulence models. Next we shall see turbulent boundary layer. The turbulent boundary layer contains three zones, that is viscous sublayer, buffer layer and log law region. We shall see in detail. Okay, consider this example. Here the flow over a flat plate is shown. Initially for some distance the flow is laminar, beyond which the flow transitions to turbulent region. And in the turbulent boundary layer we can see there are three zones, that is viscous sublayer, buffer layer and then comes the log law region. Okay. Here what these three zones represent is, in the viscous sublayer it is similar to a laminar like flow. It is very close to the wall and the Y plus will be less than 5 in this zone, and we need fine mesh to resolve this viscous sublayer in CFD analysis. The next one is the buffer layer. Here the Y plus will range from 5 to 30, and here the transition between viscous and turbulent zones occur. Okay, then the next one is log law region, where Y plus will be greater than 30 to 300. Here the flow will be fully turbulent and wall functions can be applied on this zone. Okay, so the main thing we have to remember here is there are three zones in the turbulent boundary layer: viscous sublayer, buffer layer and log law region. Okay, next we shall see how to apply Y plus in these regions. In order to determine how to apply Y plus for different turbulence models, we need to know about wall functions. Okay, we shall see one by one. First, let us see how to apply Y plus in laminar flows. In laminar flows, there is no turbulence, so there is no turbulent boundary layer present. Therefore, Y plus is not required. Instead, we have to at least allocate 10 to 20 cells in the boundary layer region. For laminar flows, the boundary layer height is given by 5x by square root of Reynolds number at the particular location. Okay, so here within this boundary layer delta, you have to specify at least 10 to 20 cells. This is for laminar flows. Next, coming to turbulent flows, we can either specify near wall resolution or we can use wall function approach. Okay, in the near wall resolution, we have to specify Y plus less than 1 or less than 5 in CFX to resolve the viscous sublayers. Here we can see the mesh is finely distributed near the boundary layer. Here the Y plus will be less than 1 to resolve the near wall region. We know that fine mesh is required near the wall, and the turbulence models which need Y plus less than 1 are SST K omega, SA, that is Parra-Talmaras, LES and DNS models. We will see about these in detail. Next, if wall function approach is used, we have to specify Y plus in the range of 30 to 300 and there will be coarse mesh near the wall. This is used for high Reynolds number turbulent flows. Empirical wall functions are used to approximate the near wall region. For example, standard K epsilon models uses wall function approach. Here we have to specify the Y plus beyond 30, so the solver will automatically approximate the wall function near the boundary layer. The boundary layer zones are shown here, that is viscous sublayer, buffer layer, log law layer and the outer region. Here if we distribute the elements in the viscous sublayer, that is less than 1, then we can capture the viscous sublayer followed by buffer layer and log law layer. If you are using wall function, we have to directly specify the first cell in the log law layer and then keep increasing beyond that. This is all about Y plus and wall functions. Next we shall see turbulence models. Turbulence models are the mathematical models which are used to simulate the effects of turbulence without resolving all the turbulence scales. Here the turbulence involves chaotic eddy-like motion across a wide range of scales. This cannot be directly solved using CFD, so we are using mathematical models. And the turbulence models provide a practical way to simulate the real world turbulent flows. Okay. Next we shall see some common turbulence models available. The first category is RANS models, that is Reynolds average Navier-Stokes equation. There are several models in this category. We are showing only 3 as of now. The first one is standard K epsilon model. It includes a wall function. Therefore, you have to place the y plus around 30 to 300. This K epsilon model is good for external and internal flows, and it captures the main flow properly. Next is standard K omega model. Here there is no wall function, so you have to specify the y plus close to 1. It is better for near wall flows as it captures the boundary layer properly. The next is SST K omega or shear stress transport K omega model. This is a blend of K epsilon and K omega model. Here we have to choose y plus close to 1, and it combines both the effects of K omega near the walls and K epsilon model in the far field zone. This SST K omega model is commonly used in industry. Next we shall see some high fidelity turbulence models like LES, DES and DNS models. Let us see one by one. LES represents large eddy simulation, where this model resolves large eddies and models the small scale turbulence. It is accurate but computationally expensive. Here you have to use y plus close to 1. Next is DES, that is detached eddy simulation. It combines RANs near the wall and LES near the bulk flow. It balances the accuracy and the computational cost. Here also you have to use y plus approximately close to 1. Next is DNS. This is direct numerical simulation. It resolves all the turbulence scales and it is extremely high because you have to use y plus, which is far less than 1 in this case. That is, the mesh should be extremely fine to capture all the turbulence scales. DNS is mostly used in academic research for simpler geometries. Alright, we have seen a quick introduction about turbulence models and y plus. In the next lecture, we shall see about conjugate heat transfer analysis. Thanks for watching this video. I will see you in the next lecture.